If I show you this ball and tell you that there is something inside of it, you will immediately ask what?
That's what scientists started asking when J.J. Thomson discovered the electron and proved that the Dalton's atom was the most elementary thing that existed. Many other scientists have contributed to this trend over the years, a particularly hard thing to do considering that, in many cases, the particle's existence was only proven a long time after its theory was made.
But I am getting ahead of myself. Let's go back. Remember the ball I had? Well, scientists came upon the conclusion that the best way to figure out what was inside of the ball was to throw two balls together and examine the leftovers. Clever, right? Of course, the mechanism used by particle colliders is much more complex, but the underlying principle is the same. So, let's get down to the fundamental question. How do particle colliders work? There are two types of particle colliders, but today I will only talk about the circular one, as it can achieve much higher energies than the linear one.
We need to keep in mind that electric fields can only accelerate charged particles. This is because only these particles will be affected by electric and magnetic fields. Initially, an electric field will remove electrons from the nucleus of hydrogen atoms. Next, other electric fields located around the particle accelerator will change from positive to negative at specific frequencies, so to concentrate these protons in closely spaced bunches. At the same time, radio frequency cavities, also located around the particle accelerator, emit a specific radio frequency that resonates with these particles, allowing them to accelerate even more, till very close to the speed of light. To make sure that the particles stay in path, electromagnets create the necessary magnetic force that guides the protons and keeps them from straying off path.
This process happens in both directions inside an ultra-high vacuum metal pipe, so as to ensure that the protons have an uninterrupted flow until the moment where they collide at very high speeds and energies at a specific point called a detector. But how are these particles detected?
The detectors in a particle collider are arranged so that they can measure all of these quantities. Firstly, tracking devices will allow scientists to see the path that charged subatomic particles will take the moment they are formed right after the collision, which, due to the magnetic fields involved, are always circular paths with different curvatures, enabling them to calculate momentum. To determine the mass, scientists will need to determine the velocity, which is achieved by measuring the angle of projection of a specific type of radiation emitted by the charged particles. To better determine the identity of the particle, calorimeters will measure the energy particles lost as they pass through this device while halting their motion in the process. There are various types of calorimeters, but their functions lie around these principles.
And that is how particle colliders work, namely the world's largest, the LHC. Now, you might be wondering why the LHC is such a big deal when talking about this field, and that is because this collider was able to generate a collision of two protons at the highest energies ever achieved in the laboratory, which led to the ultimate breakthrough of particle physics, evidence that the Higgs boson isn't merely a theory. This allowed scientists to complete the gaps of the Standard Model, a table which, much like the periodic table but with fundamental particles, tells us what everything is made up of. However, the underlying structure of this table is still far from completely understood, and so the work for particle colliders from all around the world is still very far from over.